Our toolbox thus far in the semester consists of only 3 tools. And these are the things that we're actually going to reach for when we need to do physics. I think last time I labeled them K1, K2, K3. So we have 3 tools that we're going to use for kinematics. We have velocity as a function of time and acceleration. We have position as a function of time, acceleration, and initial velocity. And that is definitely K2 and not K1. And then lastly, we have a time-independent kinematic, which gives you the square of the velocity as a function of the initial velocity, acceleration, and distance. Okay, so that's our toolbox this far in the semester. Our method is going to stay the same for basically the entire semester. So our method is always going to be start with a picture. Because even a picture often illuminates what is going on in the problem in ways that you do not expect. We want to be specific about what coordinate system we're using, which direction is x, which direction is y. If there are any vectors present in the problem, we want to break them down into x and y parts based on the coordinates that we chose in part 2. And then fourth, when I say do the physics, I mean go into our toolbox and pick out the appropriate tool for this job. Lastly, do the math. And if that seems like kind of an offhanded comment for what is frequently the largest part of the problem, I mean, this is a physics class, so we're going to focus on steps 1 through 4, and I'm just kind of, for the most part, I'm going to assume that you know how to do things in step 5, although particularly interesting bits of algebra or calculus will get highlighted as we go. Any questions about this? This is a review of what we talked about on Tuesday. Mr. Tejeda, what is deceleration? That's just acceleration in what we have defined as the negative direction. All right. Any other questions before I move on? So very frequently, in fact, most of the time in this class, we are mostly going to have acceleration be a constant, right? Not a function of time. And why is this? So part of the reason is because it leaves us with such a nice set of kinematic tools here. So if acceleration is not constant, these 3 tools are not applicable. The other reason why we might not want to do that is because the math gets complicated quickly. So we are shortly going to consider projectile motion. We will be neglecting air resistance almost completely in this class. And the reason for that is if we want to write down the movement of something in the x direction, that's actually pretty easy. So The x position as a function of time is going to equal the initial x position plus the initial velocity in the x direction times time plus 1/2 acceleration in the x direction times time squared. Our topic for today is actually free fall situations and situations involving gravity. Near the surface of the Earth, the acceleration due to gravity can be said to have a constant value. So we have little g for gravity, and the acceleration vector produced by gravity, assuming I can draw a straight line, but assuming our y direction is straight up and down, and our x direction is horizontal, then the acceleration vector produced by gravity is nothing in the x direction, and it's minus 9.8 in the y direction. So that shouldn't come as a shock to anybody that gravity pulls you down rather than to the right or up. But this is something that we do want to be explicit about. So if we are only under the effects of gravity, right, we can rewrite this kinematic equation in the x direction as our initial position plus some amount of initial velocity times time. It becomes a really simple linear equation. Now, if we want to include air resistance, which we will not, again, for this class at all, the resistance of air as something is traveling, which we will call, say, R. So the amount of acceleration due to air resistance, and I won't say equal, I'll say depends on. It depends on the cross-sectional area of the object, which would be annoying to calculate, but it's something we can definitely do. There's some constant factor, like 1/2 or 1/3, so not all of the surface area counts. And then lastly, there's the square of the velocity. So the faster an object is moving, the more air resistance it experiences. Which means if we were going to write down our position formula, we would have to write, well, now our formula looks something like this. We have some initial position, then we have plus, and I'm going to use derivatives to write down velocity. So the derivative of position with respect to time, evaluated at t equals 0, plus another term which actually depends on the derivative with respect to time squared. So you will eventually get the tools to be able to handle questions like this, but if anyone is wondering, like, well, why aren't we including friction or in this, or why aren't we including air resistance? Well, this is why. Because you end up with an equation where the value of the value of the displacement depends on its derivative and the square of its derivative, and you need some training in differential equations to be able to handle that. So in this class, we're not going to worry about this. Okay. Any questions so far? All right. we're going to return to a simpler formulation here. There's one very important thing that we want to learn in this section. This is section 3.5. That we want to learn about orthogonality, right? And this is something we all kind of know. Like, what do we mean by perpendicular? Like, x is perpendicular to y? Well, yeah. So we say that the x direction is horizontal and the y direction is vertical. Is that all that we mean by perpendicular? So there's a deeper meaning at play here. Anyone want to venture a guess as to what perpendicular or what orthogonality actually means? It's more than just being at a 90-degree angle from something. Right? What does it mean that x is orthogonal to y? Anyone want to speculate? So they are at right angles, but there's a deeper meaning to it.
Does it have something to do with the parallelogram rule?
No, but I like where your head's at. So what I'm getting at here is that x is independent of y. So if two quantities are orthogonal, they do not affect one another. So if this is our setup with y in the vertical and x in the horizontal, does gravity have any effect on movement in the x direction? Right? No effect at all. Yeah. So gravity has absolutely no effect on the x direction. So we're going to start our first problems that we deal with are going to end up being two one-dimensional problems. For example, let's do one together. Let's say that you are on top of a cliff and you are extraordinarily bored and you're just chucking rocks off a cliff. And to keep it simple to start out with, we're going to say that you just chuck these rocks horizontally. So there is some initial velocity only in the x direction. You also know the height of the cliff because you have a guidebook for this area. And this is a 25-meter cliff. How fast do you think we can chuck a rock? Let's see. Addison Sorka, how fast can you chuck a rock?
Let's say 10 meters a second.
10 meters a second? Seems really reasonable. That's something like 25 miles an hour. So while you'll never play, you never be a fastball pitcher in the Major League Baseball at that speed, it's still pretty respectable. Okay. So you chuck a rock 10 meters a second. My question is, how far from the cliff will you land? All right. So remember that we have a method that we want to follow. And right here, this is step 1. We have drawn a picture. we've already specified our coordinate systems. What's step 3? Jacob Latif, what's step 3? Nope. Nothing from Jacob? Okay. Jaden Davis, what's step 3?
Find the drop.
You're jumping the gun a little bit there. One more try. Kelly John, what's step 3 in our method? Vectors. Yep. Jaden McHenry. You have 2 Jadens in the class. All right. McHenry, you're right. Step 3 is vectors. So if vectors need to be broken down, we want to do that first. We have a few quantities here, but they're all already written in either entirely in the x or entirely in the y direction. However, it doesn't hurt to write them down that way. So our initial velocity, we will write as 10 in the x direction, 0 in the y direction. We can write our initial position as 0 in the x direction but 25 in the y direction, right? Because we are starting 25 meters above the ground. Similarly, we can write down our final position as some amount in the x direction and 0 in the y direction. And we can write down the acceleration that we're experiencing in this, that our rock is experiencing in this situation. It is 0 in the x direction, and it is, say, minus 9.8 in the y direction. Except I'm not going to write down 9.8. To start off with, I'm just going to write g. And the reason for that will become clear in a moment. But what I do want to say is that when you are first starting on a problem, don't plug in numbers until the very last step. And the reason why we don't want to do that is because we want to be able to debug our solutions. If something went wrong, it is easier to see what went wrong looking at symbols than it is looking at numbers that we may have multiplied or added together already and gotten things jumbled. So if we don't plug in numbers till the very last step, it becomes easier to debug. All right. So picture, coordinate, vectors, and this is what I refer to as our mise en place. So we've got everything in its place. We are ready to do the cooking. So step 4, physics. So we don't have very much in our toolbox. We just have 3 things. The things that we know about are initial velocity, initial position, and acceleration. We would like to know about final position. So take a moment, look at our toolbox. What do we have that relates position, velocity, acceleration? And it looks like to me that K2 is going to do the job. It's got all of those quantities that we're interested in. We may also use K1 or K3, depending on how it goes, but we're going to start with K2 because it's got everything we're interested in. All right. So here we can write down we'll start with writing down one vector valued equation. So our position of the rock as a function of time is equal to the, actually I already used x's, I'm going to use x's. So our final position is going to be equal to our initial position plus our initial velocity times time plus 1/2 acceleration times time squared. So let's take stock for a moment and think about how many unknowns are present in here. So we don't know how much time it's going to take from the initial point to the final point. Like, we don't know how much time it's going to take to make this arc. We also don't know how far out from the cliff face it's going to be. So that's two things that we don't know, two unknowns. If we have two unknowns, how many equations do we need to be able to solve for the whole thing? Right? In general. Yeah, that's exactly right. If you got two unknowns, you need two equations. Fortunately, this vector equation actually has two scalar equations hiding inside of it. So we could go ahead and write down that the x position is equal to the initial x position plus the x part of the velocity plus 1/2 x part of the acceleration times time squared. If we take a look, the x part of the acceleration is 0. So this whole term goes away. In the y direction, we could write down something similar. Oh, also, the initial x position is also 0. So the first and the third terms go away. In the y direction, we could write down something very similar. Where here, the initial y position is not 0. It's in fact h, the height of the cliff, but the initial velocity is 0. And the acceleration in the y direction is not 0 like it was for the x direction, but it's g. Negative g. So we're going to have a minus 1/2 gt squared. Okay. So we have two equations. Y is a function of t alone because we know g and we know what the initial height of this cliff was. X is a function of both time, and x is, which is what we want, is a function of time. So we could go to the y equation, solve for t, plug that into the x equation, and be done. And in fact, that is exactly what we are going to do. Right, so we'll start with the y direction. The final final value of the height is 0. The initial height is, well, we'll still write h for the moment, minus 1/2 gt squared. This tells us that t is going to be equal to the square root of 2h over g. Once we have that, we can go to the x direction. X equals initial velocity times time, which we have an expression for. And now that we're in our final step, we can go ahead and plug in numbers. So our initial velocity was 10. Our initial height was 25. And because I don't really want to pull out a calculator, I'm going to round g to 10. So inside the square root, we have 2 times 25 is 50, divided by 10 is 5. The square root of 5 is about 2 1/4. 2 1/4 times 10 is about 22 1/2. All right. Do we have any questions about how we got to the solution in this problem?
Maybe I just missed it while we were doing. So what exactly were we solving for again?
So the thing that we ultimately wanted is this distance. How far from the cliff edge will your rock land if you chuck it horizontally?
Okay.
Did that answer your question?
Yeah.
Okay. Okay, if we've got no problems there, let's actually start up for another one. I'm going to pull a question from the OpenStax book. Once again, this is from the additional problems section. So you're taking a hot air balloon ride, and like an irresponsible passenger, you chuck a coin off when you're 300 meters up. Hopefully there is nobody directly underneath you. We're going to start by drawing a picture, because that's what we do. So there's a hot air balloon. It is connected by some ropes to this balloon here. And you know it's hot because I'm going to color it in a bit with red. And then there you are standing in the basket of the hot air balloon. And there's your coin, which is falling. All right. So our coordinates there's no reason not to just use straight up and down. In fact, we don't even need an x direction for this problem because the coin is only going to go straight up and down. So we'll go ahead and say that up is the positive y direction. 3. There's no vectors to break down per se in this problem, but we should also maybe summarize the information that we've got. So the initial height that we are at the beginning of this problem is 300 meters. The initial velocity is 10 meters per second. And the acceleration that the coin is experiencing is minus 10 meters per second, where I've just decided to round g to 10 because 9.8 looks messy. Any questions on the setup for this problem?
When we're solving problems like this, is it okay for us to round to -10 as well? Or should we be using 9.8?
Yeah, it's absolutely okay to round. What I'm going to be looking for in this class is actually your ability to think through problems. It's the method that I'll be grading you on, and not the number you get on the end. So if you're rounding to make things easier or quicker, go right ahead. There's people joke about physicists liking to round pi to 5. I'm not quite that bad, but 9.8 to 10 I think is perfectly okay. All right, so here's our mise en place, our setup for this problem. It's time to start cooking. All right, so let's take a quick glance at our toolbox. Notice we've got information about the initial y position, the initial velocity, the acceleration. We want information about the maximum height reached. And we want information about the time it takes for y to be equal to 0. So once again, it looks like K2 is a pretty good bet here, it's going to involve distance, time, and acceleration. So let's start with that. So we can write down our height as a function of time is going to equal our initial height plus our initial velocity times time plus our 1/2 our acceleration times time squared. Let's take stock. How many unknowns are there in this problem? Well, we don't know so if we're looking for max first, so let's look for max height, right? Our maximum height will equal our initial height plus v naught t, and I'm going to write minus 1/2 g t squared. So we know what g is. We know what our initial velocity is. We know what our initial height is. We don't know the time, and we don't know the maximum height. So that's 2 unknowns. Unlike with our last example, we don't have another dimension that we can move to. Like, we can't just write down the same thing for the x direction and have 2 equations, 2 unknowns. So what should we do instead? Let's see. Who have I not been calling on? Calderon? What do you suggest? Derby Calderon? How about Matthew Cortez? Right? How are we going to get another equation to solve for our second unknown? All right, nothing from Matthew. So the answer is we can go back to our toolbox. Right? We've got two other kinematic equations that we can use here. So let's actually pull out K1. So the velocity, right, at max height is equal to the initial velocity plus plus acceleration times time. So acceleration being minus g in this case. So at first glance, it doesn't look like we've actually improved things because t is still an unknown in this second equation, but now we've introduced a variable, the velocity at max height, and we don't know that either, do we? Like, do we just now have 3 unknowns and 2 equations? So, does anyone have an idea what the velocity at max height is going to be? Polar Cat, what do you think? Calderon says that it's going to be 0. So, Josu Calderon. We have 2 Calderons in this class? Okay.
You can say Joshua. It's in English, or Josue.
Josue, I am sorry. And for the rest of you, I will probably mispronounce names on a regular basis. But Josue Calderon. So, you're right. It's going to be 0. So if we're at our maximum height, and so if we were at our maximum height, say our maximum height is here. If we still have a positive velocity, that means we're still headed up, which means a moment later we'll be here. So this wasn't our maximum height at all. Right? Likewise, if our velocity was going down at our maximum height, it means that a moment ago we were up here. So this wasn't our maximum height at all. So the only possible case is that at our maximum height, our velocity is neither up nor down, but is in fact 0. And this lets us solve for how much time it takes to get to our maximum height. Okay. And in this case, the math on this is quite convenient, actually. So this is 1 second. So now that we know that the time it takes, so for 1 second after we release the coin will actually continue to ascend, even though it'll be below our field of view, because the balloon is ascending faster than the coin. So for 1 second, it will continue to get higher. And the maximum height that it'll reach, well, now that we know the time, we can go back to our expression for maximum height. And that's going to be, our original height was 300. Our original velocity was 10. We're going to keep that for 1 second. And we're going to be subtracting off the height we lose due to acceleration. Right, so our second term is 10. Our third term is 5, so minus 5. So this whole height is going to be 305 meters. All right. Any questions on part A here? For part B, we want the position and velocity 4 seconds after being released. So we can actually start from our kinematic 2 that we've already written down. So part B, what is, our height at 4 seconds after release? Well, so our height at 4 seconds is equal to 300 plus 10 times 4 minus 1/2 10 4 squared. Which ends up being 300 plus 40 minus 80, 260. That's a 10, not a 16. And our velocity at 4 seconds is initial velocity minus gt, which is 10 minus 10 times 4. So here we're going to get negative 30. What does it mean that we got a negative number for our velocity here? Katja, what do you think? No guess? All right. How about Roberto Morales? What do you think that a negative velocity means? Prada guessed that it means decreased speed. A negative acceleration would mean decreased speed. But yeah, a negative velocity means it's going the opposite direction. That's right. So at the beginning of the problem in step 2, we said that up was positive. So if we get a negative number for velocity, it means we're not going up, we're going down. So after 4 seconds, the coin is actually falling at a pretty good clip. All right. One last bit, and here I'm actually going to need some space. So we're going to go to a new layer. So the last part of the question asks how long before it hits the ground. So here, use our same K2, y equals y naught plus v naught t plus 1/2 at squared. If it hits the ground, though, that means the height is 0. So we're going to have 0 equals 300 plus 10t minus 5t squared, where the 5 is just the g over 2. So how are we going to solve for t? We could try to factor it. Start by dividing everything by 5. So we have 0 equals 60 plus 2t minus t squared. Maybe we multiply everything by -1 as well to make it a more standard form. So we get t squared minus 2t minus 60. But to factor that, now we would need some values that multiply together to get -60 and add together to get -2. At least to me, it's not obvious how we would do that. So is there another way that we could solve this equation? That's right, Ramsey. You can use your third favorite equation, the quadratic equation. So remember, the hypothesis for the quadratic equation is that if you have something of the form ax squared plus bx plus c equals 0, then x equals minus b plus or minus square root of b squared minus 4ac all over 2a. So we can make some identifications with our situation here, and we can say that t is going to equal, see, our coefficient of our linear term is -2, so we get 2 plus or minus the square root of 2 squared, which is 4, minus 4 times a times c, -60, all of that over 2. So on the radicand here, we've got 4 times 1 times 60, which is 240. The negative signs cancel, so we get positive 240. So we have a 244 under the radical. And 244 is definitely not a perfect square. But 244 is close-ish to 256, which is the square of 16, and then approximately the same amount in the other direction. It is 225, which is 15 squared. So I'm going to say this square root here is about 15.5, because it's about halfway between 15 squared and 16 squared. So 2 plus or minus 15.5 over 2, which is going to be 1 plus or minus 7 3/4. So we'll get negative 6.75 or positive 8.85. All right, what does the negative answer tell us here? Because obviously we're going to take the positive number, right? The coin's going to hit the ground 8.75 seconds after we drop it from the hot air balloon. But what does the fact that we got a negative number mean? Yeah, Ramsey, you're on the right track. If we take a look at our equation for y, this is the equation of a parabola, right? And we've just kind of, like, our bias is just telling us that only positive values of t are correct. But if we were to graph this thing, it would look something like this, right? Here's the point where we dropped it, t equals 0. If we were to backtrack this shape, we would find that 6.7 seconds ago, it would have been on the ground, and 8.75 seconds in the future, it'll be on the ground. Right? So the mathematics doesn't know that time started here at t equals 0. All it knows is this shape, and you've asked to find the roots of this shape. So we need to use our common sense to interpret the mathematical answer after we've got it. So yeah, so in this case, the negative number means that if the coin had been following a trajectory rather than being dropped, it would have been on the ground 6.75 seconds ago. Right? And it'll also be on the ground at 8 3/4 seconds in the future. Any questions about how we finished off this problem? Questions, comments? Right. So for next week, we will be doing Chapter 4. Chapter 4 has no new tools for our toolbox. It's the same exact stuff. We've got, we're still going to be saying that velocity is the derivative of position. We're still going to be saying that acceleration is the derivative of velocity. We're still going to have these 3 kinematic equations in our toolbox. The only difference is we are going to be explicitly considering problems that are all in multiple dimensions. So we're going to be breaking out some trigonometry to break down vectors. We're going to be considering trajectories at an angle rather than just chucking a coin straight off a cliff. So yeah, we'll be considering more complicated projectile motion, but there's no new physics for next week at all. Any let's see, but do read Chapter 4 over the weekend. It is relatively short, and since there's nothing really new in it, I'm hoping that we can actually knock out all of Chapter 4 by the first half of next Wednesday's class, and that we can start on Chapter 5 the second half of next Wednesday. Right. So do Chapter 4 of the weekend, do some problems. I'll be adding some more problems to Expert TA. Do we have anybody that's using Expert TA, by the way?
I'm trying to, but it's just a little lengthy is all. And I don't know if the toolbox kit that we, like the 3 kinematic equations we have, all can work properly for solving them.
So the first assignment on Expert TA was just about vectors, I think. So we didn't actually get into kinematics on that yet. So I'm going to be posting questions for 2-dimensional kinematics over the weekend. That'll get you worked up there. So yeah, the first assignment on Expert TA was just math.
Well, yeah, but I mean, what do we use to solve those problems? Like, how do we know which formulas to use to solve those?
So that actually brings up something that I wanted to mention. Starting this week, we're going to be doing tutoring time. So besides teaching this class, I'm also going to be, taking a couple hours out of the week on Tuesday and Friday to just answer questions that people have, whether it's from the book, whether it's from expert TA, whether it's things that they didn't understand in the lecture. So tomorrow let me double check my schedule. Tomorrow from 1 to 3 p.m., it'll just be homework question answer time. You can bring whatever you've got, and we will work whatever problems you bring. We'll be doing the same thing on Friday from 9 to 11 a.m. So if you have questions and you don't you don't understand how a question is going, that time is just for you to ask those questions.
Okay.
Is that all right?
Yeah, no, I just I don't know if it's just me or what, but like I feel like I sort of get what you're doing when you do a lot of these problems, but at the same time I feel like there's just a lot of stuff that happens that I know the math that's happening, but I don't know why it's happening or like where you might be getting certain things from. So I don't know. Maybe I'm not seeing it as clearly. Maybe
Okay.
I need to read up on the textbook again. I don't know.
Yeah, so all of the questions that are on Expert TA so far they're pulled from chapter 2 of the OpenStax book.
Well, yeah, I'm not just talking about expert TA. I mean, like in lecture, like there are some things. Like I didn't say anything when we got to that point because I didn't want to take time away from lecture because I don't know if my question was going to be so clear cut or not. So I wanted to make sure we could get to the material for today before I ask all my questions. But I'll try to look over what you did again today, and I guess I'll try to show up for those Q&As tomorrow.
Yeah. Please don't hesitate to ask questions. Like seriously, if you're not understanding a mathematical step that I took, chances are 3 other people also aren't understanding. They just don't want to speak up.
Okay.
And actually, so we're about out of time for class for the day, but I'm going to be sticking around. And recorders, we can talk about your question for the next half hour if you'd like.
Yeah,
and
sure.
Also, Derby is asking, can you give us the answer of the quiz? And yeah, we can totally do that really quick. If you want to go, you can go. There's not going to be any more material presented. If you would like to see the quiz solution, stick around. Oh, and Eric, the link to the Expert TA, there's a sign-up link in the discussion area on Canvas. So yeah, you'll want to find the link from there. Palencia, yep, you are right. The first lecture recording got taken down. I have since fixed that, and it should be back up along with this one later today.